So the topic that we're going to study now is a brief introduction to the state space representation. Okay. So basically, we have been studying something under classical control strategy that was based on transfer function.
Teacher, this one comes in the exam?
Sorry, this one comes in the exam? No, no.
Okay.
Goes to the final exam. Okay. So what we are going to do now is we're going to change a bit the paradigm of modeling. Okay, not modeling, representation of the system. So now we will have a system that is represented by a differential equation where x is a vector. So the derivative of x over time is equal to a times x plus b times u. And we have a second equation that represents the output of the system, where the output is equal to c times x plus d times u. In general, and pretty much with no loss of generality, we will say that d is equal to 0. Okay, so this is kind of what we're going to have. A couple of equations that will represent the system. How is this system? X, as I was saying, is a vector that belongs to Rn. Okay, so our system has a variable that is called state variable. Where the state is the minimum amount of information that we require so we can determine how the system will evolve just with the knowledge of the initial condition and the input to the system. Okay, by the way, you already have the notes on these. And you can find them here. Okay, modern controllers is this presentation, control engineering modern. Okay, that basically is I will show it to you. This presentation here. Okay, so you have preliminaries on linear algebra, some basic concepts about the vectorial space, what is the linear combination, and so on. Okay, so everything is in here already. Okay, and I will try to explain it in an easier way or talking about it here. Okay, so x is the state variable of our system. Okay, so it contains all the internal variables that will help us to understand how the system behaves. Okay, and x over time, the derivative of x over time is the dynamical representation of the system in an nth order a differential equation. So in order to make this happen, if we have a vector x that belongs to Rn, and we remember that we're talking about systems that are single input, single output. So both the output of the system and the input to the system are just single elements, real values, okay, real functions, okay. And B, the matrix B and matrix C transposed, both also belong to Rn. So let's try to write an example. Let's write the generic structure and then we go for an example. So we will have a set of n variables, x1, x2, up to xn, and then we will have their derivative over time. So the derivative of this is going to be equal to a matrix that we call A, or dynamical matrix, times x1, x2, xn, plus the vector B, which is going to be B1, B2, all the way to Bn, times u. And in here, we'll have a bunch of elements that go from A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. So we have a matrix that is n times n. So matrix A belongs to the real numbers of n times n dimension, okay? And the output of the system is given by matrix C times X. So again, X1, X2, all the way to Xn, with elements that goes from C1, C2, all the way to Cn. Because we said that C transpose, I mean, now I'm representing this as a transpose vector, so it's a row. It's also a vector of n dimensions, okay? So this is how the system looks like. And basically what it means is that we have n differential equations, and the combination of the state variables, a linear combination of them, represent the output of the system, okay? And that the input of the system will influence each and every one or some of the state variables of the system through this differential equation. And we are representing the derivatives of the state space in terms of the internal variables and the input to the system. So for instance, we can have the derivative of x1 equal to x2 plus x3. The derivative of x2 equal to x1 plus 7x3. The derivative of x3 equal to u, for instance, where the output, let's say that is actually equal to only the variable x3. What does each of the variables mean in here? I have no idea. I'm just proposing, I'm just writing from the top of my head these variables. But all of these can be written in a matrix form, where I will have x1, x2, x3 equal to something times x1, x2, x3 plus something times u. So how do I write these equations here? Pretty simple. How many times do I have x1 in here? 0, x2, 1, x3, 1. In the second equation, x1, 1, x2, 0, x3, 7. In the final equation, 0, 0, and 0. And the input, what is the value that multiplies the input towards the state 1? 0. In the second equation, 0, and in the last equation is equal to 1. And the output of the system is equal to something like this, where it says 0 times x1 plus 0 times x2 plus 1 times x3. Okay.
Teacher,
So, yes, tell me.
where is the 4 left? Shouldn't it be on the right side array?
Which one? Sorry.
The 4.
This one.
I don't see your pointer.
Do you mean this one?
Yes.
That was intended to be a U.
Sorry. Okay.
Yeah. So it's U. So it's this one. This element here. Okay.
Okay. Yes. Thank you.
Sorry for the bad writing. But yeah.
No worries.
And then we have matrix A, matrix B, and matrix C. Okay. And of course, you can come to MATLAB and capture matrix A equal something. And how do I write this one? We can write 0, 1, 1. Oh, sorry. 1 and 1. And with a semicolon, we go to the next row. So with a space or with a comma, we can differentiate between the columns. And with a semicolon, we go to the next row. So 1, 0, 7. And finally, 0, 0, and 0. Okay. So this would be matrix A. Now, how do I know if the system is stable or not? So again, we need to determine the poles of the system. And the same rule applies, of course. If the poles are in the left side of the complex plane, then we're good. Left part stable, right part unstable. But the values of the poles correspond to the eigenvalues of matrix A. So in this case, the eigenvalues of matrix A are 1, -1, and 0. So this system is unstable. Okay. I can also capture matrix B equal to, of course, I could write 0, semicolon, 0, semicolon, 1, or I can also do something like this, 0, 0, 1, and then add an apostrophe at the end. That means the transpose of the vector B that I just wrote. Okay, so both are valid. And finally, matrix C is going to be equal to, I pretty much wrote the same, 0, 0, and 1, which refers to X3. Okay. So with this, I can determine a system. And we can put any name. System, I will call it Sistema, equal to SS of matrix A, matrix B, matrix C, and it also asks for a matrix D, which in this case corresponds to 0. As I was saying, we'll consider D equal to 0. So then it creates a variable, MATLAB, that has Sistema.A as the matrix A, Sistema.B as matrix B, Sistema.C as matrix C, and Sistema.D as matrix D. And of course, we can obtain the transfer function from the variable Sistema. Okay, so as you can see, this is the transfer function of the system in this case. There's actually an error here in MATLAB because this particular system is not observable. So we have poles cancellation, and this has a pole equal to 1. So I wrote a bit of a complex one, but anyway, I can quickly fix it just for the sake of the example. Let's put a 3 in here. I put it in a different color, so when you see the nose, you see what I changed. So if I go to the definition of matrix A, then I put a 3 in here, right? Then we can redo this, the definition of Sistema, obtain the eigenvalues of matrix A, and again, we can compute the transfer function that is equivalent to this one. So of course, it is a third order system, okay, where we have 2 zeros and 3 poles. And of course, the location of the poles on the transfer function corresponds to the same as we have in here. So what would be the polynomial here? 1.33 up to -15 is 0. It's a numerical error in MATLAB. -4 and -21. So if we compute this, you see we get the exact same poles from the eigenvalues of matrix A as the root of the characteristic polynomial, as expected, of course. Okay. So this is how we can make the union of both worlds, the transfer function and the state space. But we can also make an implementation of this particular transfer function. something that you should know is that there exists an infinite amount of steady space representation for each transfer function. Okay, so each transfer function that we have can have an infinite amount of steady space representation. Okay, some are more convenient for some specific uses than others, and you will find that in the presentations, here in the presentation, and we call them canonical forms. Okay, particularly there is a canonical form that we will be using quite a lot. Okay, because in a couple of weeks we will no longer be following a constant reference, for instance. We will be following a sine wave reference, okay? Or we will be following a cosine wave or an addition of anything we want, okay? So then, of course, we can make a transformation between any transfer function to an infinite amount of steady space representation, and from any steady space representation to a transfer function, okay? I just did it in here. So I got a transfer function from a steady space representation. But let's do it the other way around. And I will select a particular representation that is called in here the controller canonical form. Okay, as you can see, this canonical form has specific characteristics, which is 0, 1, 0, and a bunch of zeros, 0, 0, 1, and a bunch of zeros, and then a subdiagonal of ones in here, and only values in the last row. Okay, and then matrix B also has a specific structure, which is 0, 0, 0, 0, and 1 in the last. And C could be anything you want. Okay, so this is how the system will be represented in steady space under this specific canonical form. If we don't have this subdiagonal and a bunch of zeros and a 1 in the end, then it is not this canonical form. Okay, so what I will do is I will take a transfer function, for instance. Let's say that it is g of s equal to s plus 2 divided by s cubic plus 7s squared plus 6s minus 15. Is this stable or unstable?
Unstable.
Unstable. We have a negative in here, okay, root Hurwitz. So yes, it is unstable. And do you remember how we will build this, for instance, with the strategy that we had to use op-amps? So we had integration blocks, 3 of them, because it's a third order system. Where here we had each of the derivatives of the auxiliary variable that we made. So this was the third derivative, this was the second derivative, the first derivative, and the signal that we had. Okay. And then we said that we would do this one times 2, this one times 1, so I will not put it. We add this, and this will be the output of the system. And in the same way, we would have these ones. So this would be multiplied by a -7. This one multiplied by a -6. This one multiplied by a +15. Then we have an addition point in here where the input comes in here. And this was the way we could build this plan using operational amplifiers, okay? But what if we use a specific set of state variables that we can select properly, okay? If I select this variable as x1, this variable as x2, and this variable as x3, then of course, what I will have is, if from x2 I make the integral and obtain x1, then this one is also the derivative of x1. This one will be the derivative of x2, and this one will be the derivative of x3. Okay. And of course, I can write these equations in here, where I'd say that the derivative of x1 is equal to x2. I mean, this one is right here, this equation. The derivative of x2 is equal to x3. Again, this is the equation that I'm referring to. And finally, the derivative of x3 is equal to 15 times x1 minus 6 times x2 minus 7 times x3 plus u, where the output of the system, I'm saying that is equal to 2 times x1 plus x2. And clearly, this representation that I have in here comes to be that the derivative of the state variables are equal to 0, 1, 0. So it's only x2, 0, 0, 1, and 15 minus 6 minus 7 times x. I'm not writing explicitly from x1 to x3, nor the derivatives, plus 0, 0, and 1 on the input times u, where the output of the system is equal to 2, 1, and 0 times x. So in this way, what I'm saying is that if I have this plant, which is G2 equal to TF 1 and 2 in the numerator, and in the denominator, I have 1, 7, oh, sorry, I positioned myself wrong in the keyboard, 1, 7, 6, and minus 15. And then on the other hand, I have A2 equal to, I'm gonna write 0, 1, 0, 0, 0, 1, 15, minus 6, minus 7 as matrix A. Then matrix, let's call it B2, equal to 0, 0, 1 transposed. And matrix C2 equal to 2, 1, and 0. First of all, if I get the poles of this function or the transfer function, roots, and the characteristic polynomial is 1, 7, 6, and minus 15. These are the poles that I have that corresponds to the eigenvalues of matrix A. 1.0427, minus 2.6852, and minus 5.3575. So looks like they're the same system. And of course, I can also get sys2 equal to an SS to create the variable with matrix A2, B2, C2, and 0. And a transfer function, I will call it TF sys2 equal to TF from sys2. that actually corresponds to the same as I have in G2. So it's very easy to obtain a steady space representation from a transfer function, just by the help of using this specific variable assignation, okay? Which becomes really helpful for when we start designing controllers, when we will see that in the next class, okay? So as you can see, basically having a matrix or matricial differential equation is having several differential equations in parallel, where we have the derivatives of the state variables in terms of the state variables and the input. So this is what we're representing here, okay? Now, it is gonna be really important that we know how to, of course, do some basic operations with matrix, addition, multiplication, that kind of things. But of course, that we understand some basic concepts, like what is linear independence? What is the span and the linear combination of a set of vectors? And what is kernel, okay? I have seen and studied these videos. They're good enough. They're not long. They're from Khan Academy, so it's fairly easy to find them. Let me see what's going on with this. Apparently there is. Okay. So yes, the videos are available. So just click on them. Okay. We cannot open internally from Canvas, but yeah, they are available. So, so my recommendation and my request to you is please study these videos that I have put in here, these 3 videos, and then we're going to take it from here next class. Okay. Because what we have now is a different representation. Okay. Now, of course, we can also make simulations with these kind of systems. Okay. So in order to make a simulation, now I want to take a stable system so it's easier to see it. So what I will do is propose a new transfer function, G3, and I will make sure that it is stable. So for instance, I will say that is S plus 1 divided by S plus 2, S plus 3, and S plus 4. Okay, so this one is definitely stable. Okay, so I will define it like that. So G3 is equal to zeta pk, or I can make the expansion of the previous polynomials, but then it's easier like this. It has no gain. We have a 0 in -1, a pole in -2, -3, and -4. Sorry. This is a comma. And we can obtain a transfer function from this. Okay. So based on this, from this transfer function, that is equal to this other that I have in here, I can obtain a steady space representation. And the steady space representation would be the derivative of x1 is equal to x2. The derivative of x2 is equal to x3. And the derivative of x3 is equal to -24 times x1, -26 times x2, -9 times x3, plus u, where the output from the system is given by x1 plus x2, being the coefficients of x1 and x2 respectively. Okay, and you can get it from the assignation that we did in here. You'll see that this is correct. Okay. So I'll use these to create matrix A, B, and C respectively for this system tree. So for matrix A3, I will bring back matrix A2, because I know that the only thing that changes is the last row, because that is the structure that I'm imposing to the system with a specific steady space representation that I'm getting. So in this case, it's minus 24, minus 26, and minus 9. That corresponds to these coefficients that I have in here. And then C3 is going to be equal to 1, 1, and 0. And B3 is actually equal to B2 that I had defined before, 0, 0, 1. Okay. If I make the step response of the transfer function G3, since it is stable, I will be able to see a value, okay, a very small value, but it is there. And this is the behavior of the system in open loop. And we can, of course, make the simulation of this. So we're going to make the simulation and make a comparison of both. So from the browser, I'll bring from the control system toolbox, I bring in here an LTI system where I will write G3, which is the system that I want to compare. Okay. From sinks, as always, we bring a scope. Then we'll put a unit step from sources. That starts in time equal to 0 and final value equal to 1. And then let's implement this equation that we have in here. And even easier, what I will implement is this one that represents all of them. So to do that, as you can see, let me just make this one a bit smaller. The derivative of a variable that is called x is equal to a times x plus b times u. So let's implement the right side. So how do I make this? Of course, that is only a multiplication. So from math operations, I can bring a gain. Gains are used to do multiplications. So I'll just make this gain bigger, double click on it, and I will select, instead of an element wise, I will select there is a matrix, and it's a matrix k times u. As you can see from the definition, the output of the block is equal to k times the input of the block. So that's what I want to do. I will connect something in here that is going to be x, and what I want in the output is a times x. It could be k times u or u times k, being u the input to the block. So I'll call this one A3. Okay. So in here, what I have is x. Okay, let's say that this is my variable x. Now, I will copy this one because it's already a matrix. I will put in here matrix B3. What is the input in here? Is b times u. Ax plus b times u. So what I have in here is actually u. And then I'll make an addition of both of them. And what is this? This is the derivative of the variable x, right? The derivative of x is equal to a times x plus b times u. From the derivative of x, how can I obtain x? So of course, I can make an integral. So if I make the integral, this is the variable x in here. So this is the input to the system. So then this is x. And of course I can plot things. I can plot the state variables, but I can also plot the output from the system. And the output from the system is c times x. So again, I copy this one. And I will write in here C3. And I multiply by x, c times x, then I'll get the output of the system. What is the input? In this case, we will use the exact same unit step. So this is the state space system. And up here we have the transfer function. Okay. So I can easily also make just these MOOCs. So I can put them together, the output from the transfer function and the output from the state space system, to make a quick comparison and see that they're actually both the same. As always, I will improve the simulation by making a really small step size. And then I can run. See, in 5 time units, we are completely in steady state, so I will just simulate 6 time units. So as we said, the output of the system in open loop is close to 0.04. That, of course, corresponds to 1 divided by, is not 4, is 2 times 3 times 4. So 0.0417. Okay. And the output in here is exactly the same. We can see the comparison of both. They're completely one on top of the other. So both represent the exact same system. But as I was telling you, from G3, I can also obtain another steady space representation. So I will call it other sys3. That I'll obtain it with the SS function from G3. So you see, this is another matrix A, another matrix B, and another matrix C. But the eigenvalues of matrix, which is other sys3.A, are the same, -2, -3, and -4. And I can also quickly make a copy of this system. And in here, I will put the other sys.A, other sys.B, and other sys.C. I will add another element in here, connected in here. So we have all the outputs shown. In the same plot. I simulate again. So of course, these look the same, but we prove in here that it's actually the same. But what happened with the state variables? The state variables in here, let's see how they behave. Let's see what happens with these other state variables. So you see, the state variables are different. because what we have in one system as called X1, X2, and X3, they just have a different representation. It's like seeing the system from a different set of coordinates in X1. Okay. So there is a transformation that can take us from the system where this is the set of state variables to the system where this is the set of state variables. And you can find a way to do that in here. We call them transformation of similitude. So if we have two linear systems, A, B, and C, and A, B, and C, they're equivalent if there is a non-singular matrix that can make this transformation. So we will not go deeply into how to do this, but we will learn how to obtain this specific matrix T for any time we need to obtain the canonical representation, the canonical controller representation, okay? So the takeaway from today is there is an infinite amount of state space representations associated to a single transfer function. And then it is very easy to obtain them, okay? So from now on, we will consider that if we already had a transfer function, or if we have a system, we can easily obtain a state space representation for it, and then we will work on it, okay? So what we'll study next class is gonna be the controllability property and the pole location in closed loop, or the state space feedback that is also called, okay? So we're gonna talk about that next class. And we're gonna make a quiz on linear independence. So please read and watch the videos, okay? And this might be one class after the exam, but please read the videos about linear algebra in this module, okay? So these are the videos that I'm asking you to read. I stop record. Yes, please tell me.
See the videos and read what exactly? I think you said read. I don't know if we have to read a chapter or.
No. I think I just meant, let me see. Perhaps I don't even know what I said. See the videos and no. That's only homework. I mean, you also have the simulation project and other stuff, but that's enough. Watch the videos on linear algebra, and then we'll do a quiz one like in 2 weeks after the I week. Okay. So we will study controllability and pole placement next class. Okay. So watch the videos. That's the main homework. We're gonna study more on this topic next class. So I stop recording now.